record. There is the three dots you can find.
Okay.
In the click there and the start recording. That option is there inside that.
Okay. Let me just have a look.
Yeah.
So on my Microsoft, I don't have that. Probably you have to set the permissions.
No, it is also there. It will likely to be. You have also that option. The three dots you can find the participant list. Then all these options are there. So video, just beside the video option, you can find three dots. More actions. Okay.
Okay.
Just click on this, and you get a list. Start recording at the just towards the bottom. You can find start recording. Yeah, that one. Yeah. Then at the towards the bottom there is start recording. Can you find this?
No.
Or you have this? Oh,
no.
You don't have. Then we will record. We will record. No, don't worry, sir.
Okay.
I'll send the recording.
Okay.
Later.
Perfect. Perfect. Thank you. Professor Mana, how are you?
Yeah, good afternoon, sir.
Okay, good to see you.
Nice.
Yeah.
After some time we are meeting.
Sure.
Yes, fine. Fine, sir.
Hello, am I audible?
Yes, you are audible.
Okay,
Ravin,
okay, sir, thank you.
can you make
Yes,
your
sir, yes,
video
sir.
on? Can you make a video on once?
Okay, sir. Sir, I think owning my video will take the bandwidth more. So
Yeah, it is on. It
better
is
to
now.
off my-
It is visible now. It is visible now. Okay, you can keep it off.
Okay.
Okay.
Sir, can I one test tell Suproja one to test his mic, her mic?
Hello,
Yeah,
hello.
yeah.
Yeah, can you hear me?
Hello?
Yes.
Yes.
Am I audible, sir?
Yes. You are audible, but your voice is not very clear.
Okay.
Okay, so how about is that clear?
Yes, Professor Bhadesia, your voice is clear. Your screen is also very clear.
Okay.
No problem. So we'll start exactly at 4:30. Okay, sir.
Okay, thank you.
Okay.
I am requesting Professor Biswajit Haldar, Mr. Loitendra Badu, Professor Madanmohan Ghosh to switch on their video.
I have Dr. Mandal, I have already switched on my video.
Some noises are coming from somewhere, I don't know.
I request Professor Biswajit Haldar.
Am I audible and visible?
You are, yeah, you are audible,
Okay.
also visible. But noises are coming from your side, Mr. Badu?
Some noise is coming, yes.
Can you make your audio on for the time being? Can you make your audio off for the time being?
Okay.
Yeah.
Professor Ghosh, Biswajit Haldar. Actually, I am not trying to show my face because my internet connection. I think that if I want to be visible, then the audio would be failing.
Okay, then in that case, you make your video off. Only audio off.
আমি আমার ভিডিওটা অফ রাখছি। আমার এখানে ইন্টারনেট কানেক্টিভিটি এমন না, আমি যদি ভিডিও অন করি তাহলে আমার অডিবল হবে না। হ্যাঁ, ওকে
ওকে স্যার, ওকে।
হ্যাঁ, ওকে।
So,
okay. I request Robin, our IIM team, IIM student chapter team. I request Robin to start.
Yes, Suproja, please start your write-up.
Yes. Good evening and heartily welcome to this webinar series organized by the Indian Institute of Metals Students Chapter NIT Durgapur in association with the Department of Metallurgical and Materials Engineering. Before moving ahead, I urge the attendees to kindly mute their microphones and switch off their cameras for the smooth running of the event. The smallest of efforts in the right direction diminishes ignorance, eliminates the inconspicuous, and perhaps makes the world around us a bit more comprehensible. Keeping in with this view, the Students Chapter of IIM NIT Durgapur is enthralled to commence its infant journey with this series of webinar. Without any further ado, I would request Dr. M.M. Ghosh, HOD of Metallurgical and Materials Department, to speak a few words about this departmental activities.
Thank you. Good evening, respected Professor Bhadesia, Tata Steel Professor of Metallurgy, the University of Cambridge, UK, and our today's speaker, distinguished guests, Professor Biswajit Haldar, Dean, Students Welfare of NIT Durgapur, Mr. Lohitendu Badu, Secretary of Indian Institute of Metals, Durgapur Chapter, my colleagues, participants, students, research scholars, researchers and professionals from outside organizations or industries who are attending this webinar. A hearty welcome to this online interaction session. Today we are glad to have Sir Harry Bhadesia, who is a living legend in the field of physical metallurgy and phase transformation in steel, as a speaker in this online lecture program. This program is being organized by our department in association with the newly formed Indian Institute of Metals Students Chapter at NIT Durgapur here. I thank our institute authorities, our director, our registrar, all the deans and all functionaries of IIM Kolkata for extending their support to organize this program. And my heartfelt thanks to the coordinator, my colleague, Dr. Arup Kumar Mondal, for his effort to organize such kind of programs. This kind of functions will enlighten our department, our institute as a whole. The Department of Metallurgical and Materials Engineering of NIT Durgapur is really privileged today to interact with such a great personality. When we talk about bulk nanostructured steel or nanobenaitic steel, the first name that would come in our mind is Professor Bhadesia. Today, Professor Bhadesia will be talking on tough, high carbon, untempered martensite, which is a very challenging area and on which he has contributed a lot. On behalf of the whole metallurgical and materials engineering family of NIT Durgapur, and on my personal behalf, I express a warm and hearty welcome to Professor Bhadesia in this online interaction session. Our department has organized several courses, seminars, etc. during the last 2 years. And during this COVID situation, the department is organizing webinars almost on a regular basis. Today's webinar is the first of a series of 4 when renowned professors or researchers from leading foreign universities will deliver lectures through the same type of online platform. I request all the participants of today's program to attend the subsequent webinars as well. I can see an overwhelming response from the participants on today's program. From the report obtained from the coordinator, this webinar has been registered by more than 500 participants, including our own students, scholars, and participants from more than 13 countries all around the globe. My heartfelt thanks to all the participants for their interest. I hope this webinar will be extremely beneficial to the participants and surely gain some valuable knowledge. We all are passing through a tough time now because of the COVID-19 pandemic, but some enlightening words from a great person like Professor Bhadesia can boost up our students and scholars for doing research on such a very important area. We all know steel is the backbone of any country, but it needs to be made more and more enhanced in properties to keep pace with the country's development. Here lies the importance of the contribution of Professor Bhadesia on steel technology. We are thankful to Professor Bhadesia for being with us as a speaker in this webinar instead of his very busy schedule. And I hope all the participants will enjoy his interaction program, and I wish a grand success of this program. Thank you all.
Thanks a lot, sir, for your delightful words. I now request Professor Biswajit Halder, Dean of Student Welfares, NIT Durgapur, to enlighten us with the role that such interaction programs plays in assisting students to learn better.
Thank you. A very good evening to all of you. As I came to know from Professor Ghosh that from 13 countries of different parts of the world, I don't know, a very good evening is directed to all of you, whether that is seeming to be correct or not. Anyway, a very good evening in the Indian perspective, I am telling, and sorry for the other participants who are, participating in this webinar, I welcome you all. I welcome you all as Dean Student Welfare on behalf of the Student Welfare section of our institute, the IIM members of all the chapters all over India, the external participants from all over the globe who are participating in this webinar, the researchers, the scholars, the professionals from different industries, and my most beloved students. I will be telling first that our institute has always encouraged the co-curricular and extracurricular activities apart from the usual academic activities. Here, the co-curricular activities, that is coming to be very important, and we have different students chapters of different professional eminent organizations and bodies which are working for long years, and the newest addition to that is students chapter of Indian Institute of Metals in NIT Durgapur, which was inaugurated on 19 September. And there, what I have iterated, I can still remember that, yes, that started with, say, lots of enthusiasm and zeal, particularly by the enthusiasm shown by and supported by Professor M.M. Ghosh, head of the Department of Metallurgical and Materials Engineering, and really the zeal of young faculty Arup Kumar Mondol, Dr. Mondol, with his team members, pioneering his team nicely, has a zeal to work on it, and that is reflected by the series of seminars they have, say, promised in a row, the first of which is being organized today. And we are really lucky, though I am not an expert in this field, but still, Sir Harry Bhadesia from Cambridge University, we are really fortunate enough to greet him for this webinars, series of webinars, what is going on. And he is, as introduced by Professor M.M. Ghosh himself, he is the world expert, renowned expert on the field of theory of solid state transformation in metals, and in particular steel. So all of us would be eagerly awaiting for his illuminating speech. And here I'll be telling that in these co-curricular activities of the students, that is important, and that is important, as important is the curricular activities, because from these co-curricular activities, they are getting the taste of what is going on in the research areas outside, when they would be stepping outside of this institute to join the professional field, research field. What is going on there, the taste, the knowledge of that one, they can have as a student, and as the budding engineers, they can have the share. And this IIM students chapter is opening up that opportunity to them. And when they are getting the contact of the personalities like Sir Harry, I think they would be immensely benefited. And again, I'll be putting some rider here that with one interaction that should not be finished. And Sir Harry, I would be thinking that all the students would be liking to make a live contact with him, so that we can ever be enriched by his guidance in future also. Here I will be telling particularly about the research area, when that is categorized at the PhD research work. Of course, that is coming to be most important, because that is staged for 3 years and more. But with respect to that one, the BTech projects, MTech projects, they are by no means say inferior, because I think at the BTech and MTech level, the projects which are taken up, they are having the liberty of, say, no constraints at all. That is not restrained or chained by the say economic constraint, how much it would be the cost of the product, of the process. They are not chained by the ultimate goal, whether that is coming to be achievable or matched with the present need of the society production. But that is a way of fulfilling the dream, which may be seemingly irrelevant today, but in future, who knows, that is coming to be a cutting edge technology or mother of cutting edge technological step, say, which is coming as a dream of some young budding teenage engineer. So always we see these co-curricular activities in that way, and expect a lot from this, say, interaction with the outside world as a student chapter, which is localized in NIT Durgapur. Again, I am telling that I am really thankful to Professor Ghosh, to Professor Mandal for giving me the privilege to present my view on the occasion, which is coming to be more formal from the institute level. And again, I welcome all the participants, all the viewers, listeners, and together with that, I heartily greet and welcome Sir Harry for his, very valuable talk, which would be there in the present webinar. Thank you all.
Thank you, sir, for your words and being tender towards us. Now I request Mr. L. Badhu, Secretary of IIM Durgapur Local Chapter, for saying few words regarding activities IIM Durgapur Local Chapter.
Yeah. Thank you. Am I audible? Am I audible?
Yes,
Yes, sir. Yes, sir.
Okay. Yeah. Thank you very much for giving me this opportunity to address all of you and in this very much very interesting technical talk sessions. And respected Professor Bhadesia Sahib and Dr. Ghosh, Dr. Haldar Sahib, Dr. Mandal, and very dear, my dear students, research scholars, and other dignitaries who are online with my IIM members also. Some of the members are also online. So I'm very. It is really very. It gives me a lot of pleasure. We started on 19th September. Now we are here. Now maybe a couple of lectures we have organized through NIT student chapter. So this gives me a lot of pleasure because we are organizing, because we are organizing for the students who are the backbone of our country, and particularly for this metallurgical profession, such an interesting profession, and everything you imagine, it moves on material. Everything you talk about computer, we talk about mobile, we talk about agriculture, we talk about economy, you talk about anything, it moves on material. First of all, you need material. So that is metallurgy. So that Professor Bhadesia Sahib definitely will elaborate what he has for us, and the very interesting topic he has organized, and we'll be listening along with the students. I'm very much happy and delighted that students are coming and participating, and such a beautiful lecture has been organized, and student chapter is really flourishing with support from our parent chapter, Durgapur. I am the secretary of this chapter, main chapter, Durgapur chapter. So it gives me a lot of pleasure, it gives me a lot of satisfaction that we are doing something, giving back to the society, giving back to the students who are the backbone of our country. Really, I'm very happy, honored for the contribution by NIT faculties like Dr. Haldar, Dr. Ghosh, Dr. Mandal, Director Sahib, and all this. Really, I'm happy, and especially a big thank you for the students who are coming in large numbers and participating. Really lovely, all of you. Let's have a very good lecture here now. Without wasting much time, let's start. Thank you very much.
Thank you, sir. Thank you, sir, for your charming words about IIM local chapter activities. Finally, we move on to today's technical session, which we all have been eagerly waiting for. We are extremely glad and grateful to have Professor H.K.D.H. Bhadesia grace the occasion with his presence. The topic of his talk today is Top High Carbon Martensite. Professor Bhadesia is an Indian-British metallurgist and Tata Steel Professor of Metallurgy at University of Cambridge. He pursued his bachelor's degree from City of London Polytechnic and completed his doctorate from University of Cambridge. Following his PhD, he worked as a Science Research Council Research Fellow until 1981 and has been a part of academic staff at the University of Cambridge since then. He is the author and co-author of more than 650 published papers in the field of metallurgy and several books. In 2006, he was awarded the Bessemer Gold Medal by Institute of Materials, Minerals and Mining for outstanding services to the steel industry. He established and took the lead of new SKF University Technology Center between SKF and the University of Cambridge to conduct research in the field of physical metallurgy of bearing materials over the period of 2009 to 2019. During 2005 to 2018, As the founding director of Computational Metallurgy Laboratory, he helped create the Graduate Institute of Ferrous Technology at Post-Tech in the Republic of Korea. He has served as the editor of following prestigious journals like Material Science and Engineering A, Material Science and Technology, Science and Technology of Welding and Joining. Moreover, he had a tremendous research experience and has published a lot of journals. He was also been awarded with the prestigious fellowships like FRS, FRNG, FIMMM, FANE, Bessemer Gold Medal, Fellow of American Welding Society, Foreign Fellow of Indian National Academy of Sciences, etc. His research is mainly concerned with the theory of solid-state transformation in metals, particularly in multi-component steels, with the goal of creating noble alloys and processes with the minimum usage of resources. It is impossible to describe his achievements during his professional career and contributions to our society through the field of materials in work. So without any further delay, I would like to invite our honorable guest speaker, Dr. Harry Bhadesia, sir, to share his words to us. Please, sir.
Okay, thank you very much for your kind words. Okay, thank you all very much for your kind words. I hope you can all see my screen. I'm going to
No,
talk.
sir, it is not visible.
No, your video is on, but you have not shared screen.
Okay, let me. So I think somebody has changed the settings. So I need.
It has come. It has come. That's fine.
Yes.
Okay. Okay. So first of all, thank you all for these kind words. But my favorite thing is to talk, and if you invite me to talk, I'm absolutely delighted if I have an audience. Yeah? So thank you all very much, and a particular thanks to Professor Madan and to Dr. Kumar for organizing all this. Now, it's routine in undergraduate lectures on metallurgy that we explain that martensite is brittle when you quench a steel, and therefore, although it is strong, we have to temper it afterwards in order to achieve a good combination of sorry about that. In order to obtain a good combination of ductility, toughness, and strength, you have to temper the quenched martensite. So what I want to show you today is that there is a way of making untempered martensite, which is very strong, actually quite tough. Okay, so first of all, I want to explain very briefly where martensite in steels gets its hardness. So here I'm plotting the hardness versus the carbon concentration. And the really... Sorry? I didn't understand.
Professor Ghosh, please. Share is continuing. Please mute your audio.
All participants, kindly mute yourself.
Please mute. Share is speaking now.
Okay, so in this graph, I'm plotting the hardness versus the carbon concentration for two different phases. One is this quenched martensite, and this is austenite. And you can see that the effect of carbon on austenite is much less than the effect of carbon on martensite. And this seems to taper off at around 900 Vickers, even after you've taken account of the presence of retained austenite. So why is martensite so hard? Because if you have a carbon concentration of 1 weight%, then you will end up with martensite with a hardness of the order of 800 Vickers. And there will be consequences to that hardness, because hardness comes about because the carbon atoms will hinder the movement of dislocations. And if you hinder the movement of dislocations, then plastic deformation becomes very difficult. So your toughness is going to deteriorate. Now, the reason why carbon has such a large effect on the strength of martensite as opposed to the strength of austenite is as follows. Here, I'm showing you the unit cell of austenite, and this is the location of the carbon atom inside an octahedral interstice, which I've drawn out over here as well. And the thing to notice about this is that this is a perfectly regular octahedron. In other words, the distance here is the same as the distance here, which is the same as the distance here. So when you put a carbon atom inside the octahedral interstice in austenite, you get a uniform expansion. And you know, a uniform expansion has a very weak interaction with a dislocation strain field, because the purpose of a dislocation is to shear. So if the majority of its strain field is connected with shear strains rather than just a volume change. So carbon has a small effect on the strength of austenite because this octahedral interstice is regular, and therefore it causes a uniform expansion which has a weak interaction with dislocations. Now consider this, which is body-centered cubic iron. These are the iron atoms, and this is the interstice for carbon atoms. Now this interstice looks like an octahedron, but actually this distance here is different from these distances here. So if you look at this, this is like a squashed version of the octahedral interstice in austenite. That means that when you put a carbon atom inside ferrite, it causes an anisotropic strain field, which has a huge interaction with dislocations. And that is the reason why carbon hardens martensite much more than it hardens the austenite. And you know, obviously there comes a point where putting more and more carbon has diminishing returns because you have effectively pinned all the dislocations. So you can expect a maximum hardness of the order of 800 to 900 Vickers in steel containing roughly 1 weight% carbon. Now, I explained to you that the consequence of getting this enormous hardness is that you will have very little plastic flow, and therefore the material will tend to be brittle. And if you look at this image, which is not etched, but here you can see a martensite plate, and there's another one over here, and it's in a 1 weight% carbon steel, and the plate of martensite is full of microscopic cracks. You can see that it's cracked every so often along its length, and here's another image showing that. So immediately after quenching, you already have a lot of microscopic cracks in your material. Okay, so that means that is not going to give you a good performance in terms of toughness. And even if you take this steel and you just put a hardness indent on it, that will cause the surrounding material to crack. So it is absolutely true that in the structure illustrated here, where I have martensite plates which are many hundred micrometers long, the plates will crack spontaneously on quenching. And therefore, your material will tend to be brittle. But let's examine this in a bit more detail by looking at literature, which was published many decades ago. So there's a classic paper by Marder and Krauss and his colleagues from 1970, looking at steels containing up to 1.4 weight% carbon. And what they found was that all the plates are microscopically cracked when you quench this material, and that the austenite grain size in the range about 100 micrometers to 1,000 micrometers doesn't make any difference. They all exhibited microscopic cracking. Then there was, shortly afterwards, there was another paper by Davies and McGee, and they looked at steels with carbon concentration up to 1.8 weight%. And their conclusion was slightly different, that if you make the martensite plates smaller in length, then the tendency for cracking decreases. Okay, so that's the first clue, that if you make your martensite plates smaller in length, and I'm not explaining how to do that, but supposing you could do that, then that would make the plates less susceptible to cracking. And it's really interesting, they also identified a role of crystallography. So many of the cracks are caused by the collision of martensite plates, which have started from different locations, and you accumulate damage at the contact point. So here you can see mechanical twinning induced in this plate as a consequence of collision with this plate. And if this martensite was brittle, then these would actually be microscopic cracks. So if you have a crystallography in which the plates of martensite make a high angle with respect to each other, so these are different crystallographic variants, then you are more likely to get cracking. Whereas if the plates tend to form more parallel, then the likelihood of collisions is reduced. And I'll come back to this point later on in the lecture. So bear in mind that it isn't just the brittleness of the plates, but how they experience the stress from the formation of the other martensite plates, and therefore the crystallography of the martensite. And later on, in 1979, there was a paper looking at steels with carbon concentrations up to 1.6 weight%, and they used an incredibly fine austenite grain size, 1 micrometer, and they found, using compressive tests, that the smaller the austenite grain size, the less there is a chance of the martensite plates cracking. And although these tests were done in compression, if you compare with a large austenite grain size, even the compression properties are not good. So the basic hypothesis that I want you to take away from this is that if you can reduce the length of martensite plates by refining the austenite grain size, then those plates are less likely to fracture during the actual formation of martensite. Now, all of these carbon concentrations are very high. You know, this is 1.4, 1.8, 1.6. And if you are serious about designing and engineering material made from steel, then you have to be able to join different bits of steel together to make an engineering structure. And what is the step steel together? It's welding. And the problem with welding is that you put in a local heat source at the junction where you want to make the weld, and that will heat the adjacent steel. And in the heat affected zone, you will end up with quite coarse austenite grains, and then you will get cracking in the heat affected zone. So here is a welded region of a high carbon steel. This is a 0.8 weight% carbon. And you can see here that you've got cracks going sometimes between the austenite grain boundaries. And the scale here is quite coarse. It's 0.4 millimeters or 400 micrometers. So these austenite grains are of the order of 70, 80 micrometers in size. And that grain growth has been caused by the heat input from the welding. Therefore, you're not going to be able to make plates which are extremely fine, even though in the original steel you had very fine plates. The welding process will cause grain coarsening, and therefore you will get cracking. So here is a task, okay? This is what we want to do. We want to design a steel with a very difficult combination of properties. We want a strength which is in excess of 2 gigapascals. That means 2000 megapascals. We want an enormous ductility, okay? 30% ductility at conventional strain rates. And we want a high ductility even at a high strain rate. We want toughness and Charpy impact at -40 degrees centigrade to be 30 joules. It must be weldable, cheap and large in all dimensions, capable of being mass-produced, and if possible, to have some capability to operate at high temperatures. Now, this is a really nice wish list, okay? But a lot of these parameters that are listed are contradictory. So sometimes you may get weldability, but you may not get the strength. Somebody is talking. Can you please stop talking? Thank you. Okay, so we want to create this very difficult set of properties in order to make a steel which has a strength of 2 gigapascals, yet is weldable, and you can make it in huge quantities. It has toughness and many other properties. So how can we do this? Well, we are going to design the steel as fully martensitic immediately after it is rolled, right? So there's no further heat treatment after that. And the only way we can achieve this combination of properties is to make the austenite grain size extremely small. Now here is a set of experiments which were done by Chatterjee, who is now at Tata Steel. And here we are altering the grain size, 410 micrometers, 124, 65, and 25. And you can see these cracks in the martensite plates. This is the unetched sample, just to show you the cracks more visible. And as we go down to a 25 micrometer grain size, the number of cracks decreases. There's one more thing I want you to notice, and that is in order to give you an explanation for why austenite grain size and the martensite plate length matters in terms of cracking. If you look at these cracks, they are kind of periodic, all right? So there is roughly the same spacing between these cracks. So on experiencing a stress, the plate has broken up into segments which are approximately equal in length. So if I now make my austenite grain size much smaller than the distance between cracks, then I should eliminate the cracking. Okay, somebody else is making noise. Okay, so if I make my austenite grain size somewhat smaller than the distance between these cracks, then these plates of martensite will not break. Now, why is that? What is the reason why the plate tends not to break if you make its length much smaller? Well, if you look at composite theory, where we put glass fibers, short glass fibers inside a matrix, then when you get to a certain length of glass fiber, which is small enough, you will not be able to benefit at all from the presence of the glass fibers inside your polymer matrix. This is because it becomes impossible to transfer stress onto a small fiber, all right? And that's illustrated over here. So if you look at the stress along the length of a glass fiber, it will have a curve which is something like this. Towards the ends, you cannot transfer stress onto a fiber of this length. Okay, so if I now make my fiber sufficiently small so that its length is basically in a regime where you cannot transfer stress onto it, then it will not break. Whereas a fiber of this length, if it's brittle, will break periodically to this length. Exactly the same principle. Okay, can you kill that noise, please? Yeah, so exactly the same principle here. If I make my martensite plate so small that you cannot directly transfer stress onto it, then it will not break, because you are in this regime where the transfer of stress is affected greatly by the ends of the plate. Okay, so let's use this principle to design our steel with very interesting properties. So here is the flow chart for the design. We want to make an extremely fine austenite grain size. I'll come back to that later. I want the grain size to be of the order of 0.4 micrometers, okay? Really small. I need it to be hard because I want a strength which is of the order of 2 gigapascals, and therefore I'm going to design it with crack-resisting martensite, which hopefully has toughness, has ductility. And in order to ensure weldability, I cannot have 1.8 weight% carbon. The maximum carbon concentration we have to limit to about 0.4 weight%, so that any martensite which is produced in the coarse austenite grains of the heat affected zone still is not sufficiently brittle. Okay, so our maximum limit is now going to be 0.4 weight% of carbon, and we are not going to temper the material at all. We are going to use the properties of the martensite in the as generated condition after hot rolling. So here is the steel design that we came up with, and to cut a long story short, we have a carbon concentration of the order of 0.4 weight%. We need to add molybdenum because in a commercially produced alloy, we will have impurities which tend to segregate to the austenite grain boundaries if we don't have the molybdenum. The vanadium is there as a microalloying element in order to control the austenite grain size during the hot rolling process. And we've got a certain amount of nickel to enhance the toughness and the hardenability, chromium as well, because we want the martensite to be generated immediately after hot rolling. Okay, right. Let me show you what an austenite grain looks like in a conventional steel. So this is the grain structure of austenite revealed by doing a thermal grooving experiment where we polish the sample completely flat, metallographically polish it, and then we heat it into the austenite temperature range, and you develop these grooves at the austenite grain boundaries, which reveals their size. And in 3 dimensions, the grains are shaped approximately like the Kelvin tetrachite dodecahedron, which consists of hexagons and squares. Okay, and the reason for that particular shape is that it helps to balance interfacial tensions, although not perfectly. It's not possible to get a balance of interfacial tensions in 3 dimensions, so this is an approximation. Now, we cannot actually produce an austenite grain size, which is 1/4 of a micrometer, just by doing this heat treatment, where we austenize and have a microalloying addition to control the austenite grain coarsening. It's impossible to produce a grain size which is 1/4 of a micrometer just by heat treatment. But there is this wonderful process where you have a rolling mill and you end up with a final grain structure which is pancaked if you use a low rolling temperature. Okay, the hot rolling of the austenite must be conducted at a relatively low temperature, something of the order of 800 degrees centigrade. So this was done by Tata Steel for the alloy that I explained, and at the finished rolling temperature, we end up with severely pancaked austenite grains. Okay, so these are prior austenite grains, which have transformed into martensite, but they are severely pancaked. Furthermore, there's an awful lot of deformation structure inside the austenite grains. So the coherent regions inside this are incredibly small. They're of the order of 0.5 micrometer. I will show you some clear evidence later. So if we leave the austenite grains in a severely pancaked state by finishing the hot rolling at a low temperature, then you can achieve a coherent austenite grain size, which is of the order of 0.5 micrometers. I emphasize the word coherent because martensite plates cannot cross grain boundaries. Okay, so if they meet formidable dislocation barriers, they will simply stop. So effectively, you've controlled the largest length of the martensite to be approximately 0.5 micrometers. And the process is wonderful. You can mass produce as much material as you want by hot rolling and by cooling, and then you end up with a coil which is then sliced up. These are images, high resolution images. The scale is 50 nanometers. High resolution images to show you the very small vanadium carbide particles which help this process. So now I'm going to show you the evidence that what we have done has achieved a very fine martensite plate size. And I'm going to show you this in a completely different way from normal. I'm not looking at the length of a plate, but looking at a single austenite grain and the crystallographic orientations of the martensite within that grain. And in one case, I'll show you the austenite which is not deformed, and the other case show you the austenite which is deformed. So this is a pole figure where we are plotting 100 poles of all the martensite plates within one austenite grain which is not deformed, right? And this is exactly where we expect the peak intensities if you follow the orientation relationships between martensite and austenite. So there are 24 variants of martensite inside this grain of austenite. Sorry, this is in the wrong order. This is the undeformed material, and the austenite grain is undeformed. And you see very little spread in orientations from the expected orientations. When we transform to martensite from deformed austenite, there's a huge variation in the orientations, and that's because this pancaked grain has been divided up into regions which are very small in terms of coherent domains, and the martensite plates cannot cross those domains, and also those domains within a single austenite grain have misorientations. So instead of generating just 24 different orientations, we have thousands of different orientations of martensite plates in one austenite grain. Now that is very good, because when you have a cleavage crack going across the structure, the crack will be deflected frequently if it encounters different plates of martensite. And also the very fine plates of martensite will not tend to crack. Now, there's an awful lot of characterization associated with this work, but I'll summarize what has been achieved. So here, for example, is the toughness, the K1C, fracture toughness, against the strength. And these are the data that we published many years ago for the bulk nanostructured bainite, which Professor Ghosh mentioned. This is the new steel, consistently with a remarkable toughness of 75 megapascal root meters. That is an incredible toughness, given that the strength is just over 2 gigapascals. Similarly, if you look at elongation, we've got more than 10 to 12% of elongation. And look at the Charpy toughness at minus 40 degrees centigrade. This material here has very poor Charpy toughness at minus 40 degrees centigrade, almost zero. Here we are in the range 25 to 30 joules, minus 40 degrees centigrade, for untempered martensite, which is very strong. Okay, so the basic principle that I explained earlier, that if you make your martensite plates extremely fine, then you will get strong martensite and tough martensite without tempering. And the second criterion is that by making the martensite form from severely deformed austenite, we are presenting any crack with many different crystallographic orientations, and that will make cleavage crack propagation more difficult. Now, of course, I mentioned earlier that we cannot actually use a material effectively or in very limited applications if we cannot weld it. So here are examples of welds on this new alloy. This is a single two-pass weld and a single-pass weld absolutely no signs of cracking. And what is more is that we maintain the hardness. Okay, so there isn't much of a dip in hardness in the region which is tempered in the heat affected zone. We want a high strength, and we maintain that even after welding. Okay, I'll just illustrate to you some of the other remarkable properties of this. Supposing we want a very high strain rate deformation because we want to use this steel for blast resistance. Now, in a university, we would test the blast resistance. So a blast is a distributed explosion. It's not like a bullet, which is a ballistic impact, but it's a distributed, very sudden load. And we simulate that by firing aluminum foam at the steel. So here is a movie. This is our material here, the new steel. And we are going to fire aluminum foil at it at 450 meters per second, okay? Now, there are two criteria on whether this is a successful test or not. One, of course, is that this steel has not failed, right? And the second is the amount of bulging that we get from here. And that is, in this laboratory test, that is acceptable amount of bulging. So just imagine, you fired aluminum foil at this at a speed of 445 meters per second onto an untempered martensitic steel, and it has survived that impact. I'll show you that once more. It's quite spectacular. Just look at it nicely flexing, okay? Right, now, another experiment that we've done in collaboration with our colleagues in Tampere University in Finland and with Tata Steel is that we subjected this steel to very severe impact and abrasion. So this is our sample here, which is rotating at a very high speed. This is a slowed down movie, all right? So it's 300 revolutions per minute. And it's impacting these graphite, granite particles, which are inside this tumbler. And you continue this test for a long time because it measures both impact and abrasion. And that is the kind of wear that you get in, for example, lorries which are transferring minerals from a mine to a location. The ore will be dumped onto the lorry, and then it will be tipped out, so you get abrasion. The dumping causes impact, and abrasion is when you tip it out. And there are many other applications where this is important. And if you look at the surface of that after the impact tumbler test, you can see very clearly these are regions of abrasion where the granite particle has basically cut the steel. And these are regions of impact where we even embed granite particles inside the material. You wouldn't be able to embed the particles if this was a brittle material. We are very excited by these tests because if we look at the wear loss in this very severe test against hardness, our material outperforms any of the commercial alloys available, okay? So this is hot rolled condition, so without any tempering. If we take the same material and we simply quench it from the austenitizing temperature so that we have these equiaxed austenite grains which are large, then look, the wear rate increases dramatically, showing you directly the consequence of having these extremely fine martensite plates in the as hot rolled material. These will not be fine and will have a lower toughness, okay? So these are all laboratory tests. And there are a lot of students watching, all right? A laboratory test is not the same as testing something in service, because the circumstances in service will not be as controlled as in a laboratory test. So you may have particles with many different sizes. You may have varieties of particles impacting on your material and so on. So what we've done is we've installed this steel in a particular part of the Tata Steel production plant in Jamshedpur. So this is a particular chute where minerals fall onto a steel plate here. And the steel plate conventionally is a mild steel plate with a very expensive hard-facing alloy, which is iron chrome carbon, deposited onto it by welding. Okay, so you can imagine that not only is the welding alloy expensive, but also the fact that you have to deposit the material on there. And eventually, you know, the mineral impacting on this will completely wear the material out. So we replaced this with our new steel, and it has been in position for approximately, you know, I'm guessing now it's approximately 18 months since it was installed, and there is no visible sign of damage. There's no hard-facing alloy put onto this. So we are examining here the most impacted area, and nothing has happened. So we now need to simply leave it in position until some sort of damage happens before I can completely claim success on this. But everything looks promising, okay? And I believe that the steel has now been installed in other locations where there's different kind of wear in the Tata Steel production plant in Jamshedpur. Now, one other example why this steel is likely to be very successful is that, look, if I look at the strength versus the Charpy plot, these are sort of ordinary low alloy steels. And if we label the cost of ordinary low alloy steels as 1, a medium alloy steel with a strength approaching 2 gigapascals will have a cost of 4. And then you have the very high alloy steels, which are like AirMet 100 and so on, with lots and lots of alloying elements. They have a cost of 8. This is our new steel. And on this scale, we have a cost of about 2. And much of this cost comes from the 3 odd weight % of nickel that we have added to this, okay? But, you know, if you get a really good service life, then a cost of a factor of 2 compared with ordinary steels is not bad at all right? So we have high hopes for this. I'm going to slightly change the subject because earlier on I said that, you know, we have 1.8 weight % carbon, 1.6, 1.4, and we're not going to be able to use it because we have to weld it. But I can tell you that there are already steels in service and in automobiles in which the martensite contains 1.2 weight % carbon without any problems, okay? And this is an example. This is known as a trip-assisted steel. TRIP stands for Transformation Induced Plasticity. And it has a mixed microstructure. This is ferrite here, which is very soft. And this is a mixture of austenite and bainite. And when we, the carbon concentration of this austenite is 1.2 weight %, even though your average alloy concentration is 0.15. And that's because when these phases, the ferritic phases form, the ferrite and the bainite, they partition the carbon into the austenite. So even though you have a low average carbon concentration, the total carbon in there is 1.2 weight %. And when you actually put this into production, you know, the forming operations and so on, this austenite will partly decompose into martensite under the influence of the stresses and strains. And that martensite is untempered with 1.2 weight % carbon, and yet we are not bothered about this. How can we cope with a steel containing untempered martensite with 1.2 weight % carbon? Well, the first thing to note is that this is a scale of 4 micrometers. So these regions are actually of the order of 1 micrometer, and therefore we are limiting the length of the martensite plates, all right? And when it comes to welding, the fact is that the composition here, the average composition, is fine. You will not produce brittle martensite in the heat effector zone, because that martensite will simply contain 0.158% carbon after that region has been fully austenitized. So obviously this material does not have a high strength because it's not completely martensitic, but nevertheless we are making good use of high carbon untempered martensite, because look, if I plot the stress austenite and the white is the ferrite, I've got enough austenite here to percolate through the structure. That means I can draw a continuous line through this austenite, all right? And austenite is a more ductile phase than martensite. So as long as the austenite can deform, I'm okay. The sample will not break. The austenite is tending to transform. So these blue regions will decrease as we strain the material. And in this diagram, we have lost percolation. If I start from this region of austenite, I cannot draw a continuous path through the austenite. Once percolation is lost, percolation means can I draw a continuous path through these red squares? In this case, I cannot. Okay. Once percolation is lost, you are actually stressing the martensite, the high carbon untempered martensite, and therefore your sample fractures. Okay. And we can calculate the percolation threshold, making certain assumptions about the shape of the austenite. And it turns out that in this structure, we would actually lose percolation at about 10% of retained austenite. So we need to design the amount of retained austenite so that there is a period over which percolation is not lost while the martensite is triggered by the trip effect. And we can experimentally measure this as well, because look, here we have a fraction of austenite and we're looking at the diffusion of hydrogen through the sample. And as the fraction of austenite increases, the diffusion coefficient decreases. That's to be expected because the diffusion coefficient of hydrogen in austenite is much smaller than in ferrite. But as soon as you lose percolation, which is at around 10%, you get a dramatic rise in the diffusion coefficient. And if you look at a duplex stainless steel where these austenite regions are isolated by the ferrite, then again the diffusion coefficient is high. Okay, so we can prove experimentally as well as by calculation that the austenite loses percolation in a structure like this when we have approximately 10% of austenite left. So to summarize again, fine, untempered, high carbon martensite can be ductile, strong, tough, and weldable. You do not need to temper it. So the carbon concentration has to be below about 0.48%. So we can revise our teaching to undergraduates that martensite does not have to be brittle if you make it extremely fine, and also increase the number of crystallographic orientations within a single austenite grain. If you have a mixed microstructure, then the martensite will fail when the austenite loses percolation. And there are now many engineering applications in which the steel contains or generates untempered high carbon martensite during deformation. I'm going to finish off with just one. In the case of the wear resistant plate, we just have to wait for several years to see its performance in the Tata Steel plant. Okay, and right now we've done perhaps about 18 months. But I'm going to show you now an example where we had many years of service, okay? In a microstructure where we have a mixture of granitic ferrite and austenite to start with, and this austenite under the influence of service will, near the surface, tend to decompose into high carbon untempered martensite. And I'm talking here about the first ever carbide-free magnetic rail, which was installed inside the Channel Tunnel connecting England and France many years ago. And it has, in April 2020, I was sent a message that 1 billion gross tons of traffic have gone over the magnetic rail without any need for grinding. Now, rails are inspected regularly, and they tend to develop fatigue cracks from the surface. So what they do in ordinary rails is that they grind some of the surface away so that the fatigue cracks are removed and they don't penetrate. In this case, we do not require that grinding because there are no hard particles to induce that fatigue. It's a very fatigue-resistant structure. And furthermore, the austenite near the surface, which gets deformed by the passage of traffic, will actually harden the surface by forming this fine, untempered martensite. So this has been in service for many, many years. I can't remember when it was put into service, but notice that this is a safety critical application, okay? So it is a real feat of engineering and metallurgy working together. So I'm going to end my lecture now, and I'll be happy if it is required to answer questions.
Thank you, sir. Thank you so much for your outstanding presentation. It was a delightful learning experience for all of us and to discover something new about this domain. I hope all the participants will be benefited from the knowledge you shared with us. With your permission, if you would like to take few questions from the participants.
I will be delighted.
Yes, sir. Participants on MS Teams may raise their hands to speak, or they may drop their question in the comment section of our Facebook and YouTube pages. Those who are present on MS Teams, they can directly raise their hand and ask a question to sir.
Yes, please ask questions as quickly as possible, because you know sir is very busy person. Yeah, I can find one hand is raised by Hassan. Hassan, please ask.
Sir, in the composition that you shared of the steel, so can we replace nickel with copper? Because nickel being expensive, could it be replaced by copper?
So one of the things is that, you know, in order to take something from a laboratory to production, we have to get it right almost the first time, okay? And then if you start making any changes to that, you have to go through a whole process of validation of mechanical properties and everything else that you've done. So what we try not to do is to modify the composition. However, if the production rate becomes sufficiently large, then you can play about with the chemical composition and see what happens. Now, copper doesn't have exactly the same effect as nickel, because nickel is known for toughening the steel, and the way it does so is that if you have a screw dislocation, it's actually three-dimensionally dissociated in ferrite, and that makes it difficult to move, and that's why we get a strengthening at low temperatures, which gives us the brittleness, the ductile brittle transition temperature. Nickel makes that faulting, three-dimensional faulting, constrict, so it actually has a fundamental effect on toughness. Copper does not have the same effect, and it is possible that if we add too much copper, then we might get problems with the actual rolling from things like hot shortness. So one of the cures of hot shortness is that you add nickel, so that would kind of defeat the purpose. But, you know, I think that the basic concept is worth exploring. You know, you could, in your laboratory, for example, make a sample in which you substitute nickel with copper and look at the basic properties as we did. Originally, we worked on something like 60-gram samples, and then scaled it up. So it's possible to explore it further as long as you maintain the martensite grain size extremely small.
Yes. Next question from Prince. Unmute yourself and ask the question.
Hello, sir. Good evening, sir.
Hello.
Sir, am I audible, sir?
Yes, yes, continue.
Yes.
So actually, like as you said, if we have to decrease the austenitic grain size up to 0.4 micrometer, and still we are having carbon combustion up to max of 0.48.
Right.
But using all this setup also, up to how much maximum length of plate we can go? Like, is it practical to go to have some good length, or like it is like lesser or what?
No, I think there's no problem in the length. The one issue is that because the martensite is produced immediately after hot rolling, okay, you have to cut it up, all right, rather than coil the material, okay.
Yes.
But there's no limitation, no reasonable limitation on the length that you can produce.
Okay, sir.
Yeah.
Thank you, sir.
Okay.
Next question is from MB Nataraj. Please ask. Nataraj, please ask.
Yes, sir. Sir,
yeah.
Hello.
Yes, sir. Good evening, sir. Sir, suppose if the carbon content is 0.04, is it possible to get the martensite?
Yes, in fact, you can get martensite in pure iron. Okay.
Okay.
So supposing you take absolutely pure iron, a single crystal of absolutely pure iron, and you cool it at about 10 to the 6 Kelvin per second, it will be martensitic, and you can see the crystal bend according to the shape deformation of martensite. And the shape deformation is what defines it as martensite, and therefore you get a plate shape. Whereas if you cool the same thing somewhat slowly, then you get equiax grains of ferrite. So yes, it is absolutely possible to get martensite in 0.04 weight percent carbon steel. Yeah, and if you do a spot weld on that, the region next to the spot weld is cooled extremely rapidly. This is a resistant spot weld, all right? So where you have a very high heating rate and a very high cooling rate, you can find martensite in the vicinity of that spot weld. It's not going to be very hard because the carbon concentration is very small.
Yeah, sir. Another question regarding martensite itself. So actually, quenched martensite and strain-induced martensite. So in these both, which one is more stronger, sir? Because martensite is martensite only, but strain-induced martensite is more stronger or quenched martensite.
Yeah. So by strain-induced, we mean that the austenite is in a deformed condition.
Yeah. Yes, sir.
And therefore,
yes, sir.
The defects in the austenite are inherited by the martensite. Yeah.
Yes, sir.
So in that sense, yes, it would be stronger. But the effect of carbon is overwhelming. So if you are talking about high carbon steels, then the martensite would be slightly stronger, but not much stronger. But in a low carbon steel, you're absolutely right.
Okay. Thank you, sir. Thank you, sir. Thank you so much.
Yes, sir. Next question from our Facebook live page, YouTube live page. What is the role of silicon in this alloy?
Yes.
Question by G.T. Janakiram.
It's a very good question. So originally, when we were working on this, we imagined, according to our calculations, which were not right, okay, we imagined that we would also get a little bit of bainite. And if bainite forms, then you really don't want carbides because they form in an uncontrolled manner in the bainitic microstructure. And the idea of the silicon was there to stop that from happening. But I think, if we were going to go through the design once again, then you may not need that much silicon because we don't actually get bainite in the structure.
Okay, thank you. Sir, next question from Sri Gaurav Kumar.
Good evening, sir. This is Gaurav from NML. So it was really nice to hear from you. Like it was a great learning experience.
Thank you.
So one point I have, like you mentioned that carbon less than 0.4 can be easily weldable. So is this 0.4 value is based on experiments or like some literature data?
So generally speaking, if you look at the very old carbon equivalent data,
Yes.
The welders use an equation which is known as a carbon equivalent. Okay?
Yes.
And in the old days, the carbon concentrations of steels used to be higher than the modern structural steels. So there's a particular equation which says, the carbon equivalent mustn't be greater than 0.4. And carbon equivalent includes the other alloying additions as well. So it's based on empirical data, not on empirical data can be very, very useful actually, because it's built on experience on welding. So that is what we have assumed. If we exceed the concentration too much, then we will get spontaneous cracking of the martensite in the heat affected zone.
Okay. So, sir, will it be more reliable to take carbon equivalent for weldability or only carbon, sir?
Strictly speaking, we want martensite in our material, whereas the purpose of the carbon equivalent was originally to stop the martensite from forming. Yeah? So we are not concerned with the formation of martensite, and it's really the carbon concentration for us that is the most important. Yeah? We actually want to generate martensite, but we don't want the carbon concentration of the martensite to exceed about 0.48%. But 0.48% is something that I cannot quantitatively justify. It's based on intuition, and you could try, higher carbon concentrations, assuming that the heat affected zone behaves itself.
Okay. Thank you, sir.
Thank you, sir. Next question from Syed Abdul Rahman.
Okay.
Syed Abdul Rahman.
Hello, sir.
Sir,
my question is that what could be the best use of such a steel when it comes to practical application, and how easy it is to synthesize such a steel?
Yeah, so Tata Steel knows how to make this, okay, and they've made many tens of tons, okay, and the particular applications that we are looking at is in wear applications, wear resistant applications, very severe wear resistance applications, where you also need to weld, because if you are constructing a vehicle, you can't just put plates on it. You have to have some sort of joining, and that part seems to be going very well. And the second part is that it performs very well against ballistics. So you fire bullets at it. The Indian Army has proven that for certain caliber rounds. It is even possible that in a thinner form, it could form body armor. Now, since we are producing this by hot rolling, our minimum thickness was about 6 millimeters, and development has to be done to see whether we can get the thickness smaller, because it has also been tested against revolver bullets. Okay, but the imagination can run wild on where you could use this, and normally you replace a particular material being used in a particular application if the advantage is sufficiently large. Okay, and in the case of wear resistance and defense applications, it would be significant.
Okay, thank you, sir.
Thanks a lot, sir.
Another question from our YouTube live. What is the role of vanadium in this alloy? Question by Venugopal Tota.
So we wanted a low finish rolling temperature to leave the austenite grains in a pancake shape. Now, if you use niobium, then niobium would precipitate at a high temperature, which is not close to the finish rolling temperature, and therefore it would be ineffective in controlling what happens at the finish rolling temperature. So vanadium carbides are less stable than niobium or titanium carbides, so you can induce them to precipitate at a sufficiently low temperature. The finish rolling temperature is approximately 800 degrees centigrade, and we designed the vanadium content to precipitate properties that can be achieved, and therefore to make the material useful. Now, In the case of a rail, there are several criteria. It's never just one thing, okay? So rolling contact fatigue has to be good. The wear resistance has to be good in the current plant that are used to manufacture the rail, because if you require capital investment to actually make your rail with a new alloy, then that reduces greatly the chances of success of that alloy. So in the case of the carbide-free magnetic rail, there's nothing expensive there. It's carbon, silicon, manganese. Yeah. But the alloys had to be designed so that they could be produced on the normal rail production platforms. Polytic rails are actually very good as well, and they also have a very low wear rate, depending on what grade you use, but they do require grinding to periodically get rid of the fatigue cracks. Now, in something like the channel tunnel, that obviously, wants to be in operation all the time. So if you can use something which is very much more rolling contact fatigue resistance, then that would be good. Yeah.
Thank you, sir.
Okay.
Sir, next question from YouTube Live. Is it possible to achieve a similar effect by reducing the martensite block or packet size? Absolutely right.
So anything which presents many different crystal orientations, all right? So if in one austenite grain you have many different orientations of packets and a small packet size, that will improve the toughness. That is well established. Generally speaking, all that work has been done on the low carbon lath martensites, okay? Simply because those are structural materials. When it comes to high carbon martensite, it doesn't form in the shape of laths and so on. They are plates. So the very first slide that I showed illustrated the plate martensite. So it does depend on what kind of martensite you're dealing with. The high carbon martensite don't form in packets as the lath martensites do.
Yes. Thank you, sir. Next question from Dr. Tarang Sinde. Unmute yourself and ask question. Dr. Tarang Sinde, please unmute. Dr. Tarang Sinde.
Dr. Mandal, myself, can I ask in this time one question?
Yes, of course.
Yes, ask.
Dr. Bhadesia, sir, in your slide number 36, you mentioned that fine untempered high carbon martensite is ductile, strong, and easily weldable. How is it possible? Untempered martensite? Is it due to fine structure or something?
Yes. So we have in Tata Steel, they've used laser welding, arc welding, and so on. And in all cases, they can achieve a crack-free region in the heat effector zone. Because don't forget, we also have microalloying additions in the vanadium in there. So we don't get a very coarse prior austenite grain size in the heat effector zone, and that's why we don't get the cracking.
Okay. Have you got your answer, Mr. Miyadat? Okay. Next question from Sairam. Unmute yourself and ask your question.
Good evening, sir.
Hello.
So my question is, in the present martensitic steel, you have shown that molybdenum addition is mainly for avoiding the impurity embrittlement.
Molybdenum, yes.
Yes, sir. So besides that, molybdenum is a good solid solution strengthener and also BCC stabilizer. And also it is a strong carbide former besides the vanadium and other carbide forms. So by increasing the molybdenum, can we increase the toughness as well as strength of this martensitic steels? Like what is the exact effect of the molybdenum concentration on the martensitic formation? Yes.
So obviously, molybdenum affects the relative stabilities of austenite and martensite, and therefore it influences the martensite start temperature, and it will have a small solid solution strengthening effect. But the main purpose is that if you make a large object, all right, then it becomes susceptible to embrittlement by impurities segregating to the austenite grain structure. Okay, so phosphorus in particular, during the cooling towards the transformation temperature at around 600 degrees centigrade, the impurity atoms go into the austenite grain boundaries, and then you embrittle the whole thing and you get austenite grain boundary failure. So to avoid that, you can add molybdenum. It's very well established from decades ago, where people studied temper embrittlement. And the mechanism is that it stops the phosphorus atoms from segregating to the austenite grain boundaries. There's a kind of a Gathering action between the phosphorus and the molybdenum.
Okay, thank you, sir. In this connection, actually another question from YouTube Live. What is the martensite start temperature of 0.4 weight% carbon steel? How essential the MS for this project?
Yeah, so we want the martensite to form immediately after hot rolling, okay? And the martensite start temperature, just recalling from memory, all right, is of the order of 300 degrees centigrade, which is fine. So we don't need it to be particularly controllable, because it's far away from any other transformations that can happen. The steel doesn't undergo any other transformations like bainite or ferrite or pearlite during the normal hot rolling and cooling process. So the MS temperature is useful, but we don't need to worry about it in this particular context. But you know, the MS temperature can easily be calculated for any particular steel using either fundamental principles or empirical equations.
Okay, sir. Next question from Sairam again.
Yeah.
Sir?
Yeah.
Sir, what is the effect of adding molybdenum at high temperatures? Like, you are also looking for high temperature capability of that alloy. So in ferritic steels, creep resistant steels, we have the molybdenum to play the role of strong carbide strengthening. So does besides preventing embrittlement, so does that also help increasing the moly?
Yeah. So our original goal was actually to also look at high temperature properties, but we became so occupied with its room temperature properties and applications that we haven't studied that at all, actually. But you're absolutely right that if you have elements like molybdenum, you will form, you know, MO2C if you temper it at around 600 degrees centigrade and so on. But we haven't looked at whether the properties achieved, therefore, in terms of creep resistance, are exceptional or not. So I can't really answer that question with confidence.
Thank you,
sir. This is M.M. Ghosh. I have a question in this connection. You know, very near to this. Suppose you are refining the martensite. You know, from austenite you are producing very fine martensite. Okay, so what will happen to the creep properties, because it's very fine martensite plates? So do you think that the creep resistance will be hampered? So high temperature application of this particular material that is will be reduced? Means it will be hampered, or what is your idea?
It's a very good question. I don't know is the answer. Okay, I think it's something for somebody to investigate, actually. And if you're interested, I can put you in touch with a colleague at Tata Steel who can provide you with a sample.
Okay.
Yes.
Okay.
We can.
Okay. Thank you.
Thank you, sir. Sir, next question from Anirban Ghosh. Please unmute yourself. Anirban Ghosh.
Good evening, sir.
Hello.
I enjoyed your presentation. It was very good, very informative. my question was, innovation of this type of steels, do we need to revisit the relation between hardenability and weldability? I mean, hardenability, it is inversely proportional to weldability. So with this kind of innovation, do we need to revisit that relation?
Good question. I think it actually has to be linked to an application. So if you are thinking about constructing, say, a pipeline, then the requirements are completely different from if you are making armor or wear-resistant plate. But it would be good to revisit, because there is now a great deal more of fundamental knowledge for the hardenability problem, and therefore you might be able to make a stronger link between that and weldability.
So will it be dependent on the orientation of martensite as we discussed? Is it like that? Is it?
Yeah, so hardenability is simply the ability to produce martensite, okay, at a specified cooling rate. And weldability means that you produce a structurally sound weld. And in this latter case, having many different orientations of martensite is a very good thing from the point of view of toughness of untempered martensite, or even tempered martensite, because you tend to deflect a cleavage crack more frequently, and therefore you get a higher toughness.
Thank you, sir.
Thank you, sir. Next question from CIO Romani. Please unmute yourself.
Hello.
Hello.
Can everyone hear me?
Yes.
Okay. You said during the presentation about the welding of this material, and I have doubt about it.
Okay.
Is it possible to use arc welding for weld this material? And if is there any material that need to be weld consumable, need to be used specifically for this welding? I mean, the gas or the welding consumable?
Yeah, very, very good question. Okay, so we can, in Tata Steel, there is a specialist group dedicated to welding, and they have tried laser welding, but laser welding, you require very good fit-ups and so on and so on. It's not really very useful for this particular scenario. Arc welding works perfectly okay, and there are two things you can do. One is use a consumable, and it's very easy to make a consumable composition by altering the coating or the core of the wire, and that has been done. But ideally, we would like autogenous welding, all right? That means you're not actually using a filler, because then you would have the same material just being joined together. And that has also been tried successfully.
Okay, I think he got disconnected.
Oh, okay.
Okay, so we can take next question. Next question by Akshay. Please
hello,
unmute.
Sir.
Yes.
Hello, sir. I am also dealing with the high strength martensite steel, which is mostly used in armor applications and involved in various high strength steel development. I was just trying to know that can you just request you to put more light on role of retain austenite morphology, shape, size, and how we can identify after deformation of that the samples like bending that martensite has the retain austenite has transformed to martensite.
Yeah.
There were two doubts in my mind.
Yeah. The very best way is X-ray diffraction, okay? Because X-ray diffraction will penetrate a conventional X-ray diffraction will penetrate about 10 micrometers of the steel and give you a quantitative assessment of the retained austenite content. And if you want a greater depth, then you can either use synchrotron X-rays or neutron diffraction. In the particular steel that I was talking about, there is basically zero retained austenite, but there are many armor steels where you need to look at austenite, and the best way is X-ray diffraction. Does that answer your question?
Yes, sir. Yes, sir. And I just wanted to know and request you to put more light on shape and the size of retained austenite in martensite. Normally, when it forms as a thin film or block, which would be a better choice to have better ductility with smaller block size and pocket size.
Yes. So basically, you want fine austenite. Even if it is blocky, if it is very fine, then that has good properties. And films are ideal, but you can't always get them, right? So in the assisted steel that I showed, they were more like blocks, but they were very fine blocks, so it doesn't matter. Yeah, but if you have coarse blocks, then you get poor toughness.
Yes, sir. Is there any specific size or anything available that up to 2 micron or 5 micron like that, which is suitable or better?
So the problem is as follows, all right? So if you have a very strong material, then the size that you should limit the austenite to must be smaller than if you have a material like a trip assisted steel, which is 800 megapascals, where you can tolerate a larger one because the ferrite is there as well. So there's no particular size that I can mention, but really you need to look at what is the strength of the material. If the strength is very high, then you need a much finer region of austenite before it becomes brittle.
Okay.
Sir, next question from YouTube Live. It is a very interesting question. Sir, in one of your book on benite, you wrote that inclusions are formed with two different morphologies, niobium carbide and titanium nitride covering each other. So what is the mechanism of its formation? This question by Sanjit.
So if I understood correctly, it's about one carbide forming on another. Is that right?
Yes.
Yeah. So the reason why one carbide forms on another usually is that it's easier to nucleate at the interface between the original carbide and the matrix, which could be austenite. So if there is a good fit between those two kinds of carbides, then it makes nucleation easier. And then you would expect some sort of an orientation relationship, a reproducible orientation relationship between the two kinds of carbides.
Next question. I think next question from Uday Bhaskar. Please ask.
The next question from here, YouTube Live. Last question from YouTube Live.
Okay.
Hello.
Sir, is there any minimum austenite fraction which these kinds of steel should have? And what limits the carbon percentage in this steel?
Yeah.
He is asking regarding the austenite fraction.
Yeah.
Minimum austenite fraction.
Right. So in a structure which only contains magnetic ferrite and retained austenite, we need the austenite to be greater than about 10% in order to get percolation through the austenite. Okay, because I said to you that fracture occurs when you're actually loading the martensite. The austenite has lost percolation. But if you have a structure in which you have lots of allotriomorphic ferrite and magnetic ferrite and then retained austenite, then the fraction really depends on the application. If you want formability, then you want austenite which is going to decompose steadily over a large range of strain so that you maintain the work hardening that's necessary to prevent the plastic instability. So elongation would then determine how much austenite you need, but it will be more than 10%. Okay. So maybe we can have one more question.
Yes, sir. From MS team, Uday Bhaskar. He is waiting for a long time.
Hello, sir. Nice presentation. The composition, whatever you have shown, is it matching with some commercial grade?
No. You're talking about the first part of the presentation, right?
Yes. Yes.
So we have created this. It is not a commercial grade.
Okay, means when I was looking at the composition, it was actually looked similar with 9310 with higher carbon percentage.
Okay. That may be the case, but this has a structure which is completely different.
Okay, but is there any method other than which means hot rolling, whatever you have said? Are you looking at where you can form this less grain size?
No. So our condition was that it must be capable of being mass produced, right?
Yes.
So we can only get that pancake shape by hot rolling. We can't get it by heat treatment alone. So we are not looking at any other process, but you can let your imagination run wild. If you can, for example, by wire drawing or something, get the same structure, then that's fine. But we haven't looked at that at all.
But what is the reduction ratio you're looking at, sir?
Oh gosh. So from memory, I can't remember, but I think the ingot itself, it must be about 4 centimeters high, and we've gone down to about 6 millimeters.
Okay, because if that ratio, if I want to maintain, means if I want to try the same steel into my components, so I need a really big ingot size and reduce it to the smaller sizes.
I think it's the step, it's the final step that's really important to get that pancake structure.
Okay, and that is happening only because of forming. Am I correct?
Yeah, because of the low finish rolling temperature.
Oh, okay. Okay. Thank you, sir.
Okay.
Sir, if you allow, last question I can ask. Otherwise, I have to stop.
Yeah, sure.
Last question by Amal Dange.
Amal Dange. Good evening, sir. Yeah, good evening, sir. This is Amol Dange from L&T Special Seals Heavy Forgings. I was actually having a question which you have partly answered from Uday Bhaskar's question. Is this composition, amicable for hot forging or open die forging application wherein the temperature gradients during processing are huge? Or is it tailor-made for hot rolling?
So I think the composition is not special except for the things that I mentioned about the role of each solute. But the properties, the good combination of properties can only be achieved if you get a very fine austenite grain size. So if you have a process in which you again end up with a very fine austenite grain size by forging or whatever, that would work. Okay.
Yes, sir. Thank you.
Sir, in this connection, one question came from YouTube Live. How to avoid ferrite formation during hot rolling?
Okay, so that is very simple. That the combination of alloying elements is sufficient to avoid any ferrite formation or bainite formation.
Okay. Thank you, sir.
Okay.
Professor Bhadesia, can I ask the last question?
Okay. Okay.
So percolation threshold, you were in connection with that trip still you talked about the percolation threshold. Okay. So does it depend on the austenite grain size?
Not so
you have
much.
talked about 10% the threshold value for different temperature you started. But does it depend on? I'm just curious to know. Does it depend on austenite? Do you think that the austenite grain size?
The actual percolation doesn't depend on the austenite grain size. It simply says, look, I need this much austenite in order to maintain continuity. Okay. The austenite grain size may influence the kinetics of transformation quite significantly, but
Yeah.
not.
But continuity, so far as continuity is concerned, the fine-grained austenite and coarse-grained austenite does not alter the that path continuity of this fine and coarse. Do not think that that will differentiate that continuity.
I think it's possible, but I was really talking about continuity within an austenite grain. Because if you go to another austenite grain, it's got a different orientation.
Okay. Thank you.
So let me just finish by saying that I have really enjoyed this. Okay. And
we are also very thankful to you. Instead of being busy schedule, you have given us time, and it's amazing. No more question, Arup, please. No, more question.
All questions.
Okay.
No, sir. We will send you the question. We are collecting the
remaining questions. I will ask the participant to send to an email, or I can pass you those questions to you. Okay. From my email. So thank you very much, sir, for your nice presentation and very informative presentation. We have learned a lot from you, and we have really enjoyed it. I think all the participants have enjoyed and has definitely have some take homes from these deliberations. And my personal request or the request from the department for you, whenever you come to India, once the situation, of course, once the situation becomes normal, you please to communicate me, and I will definitely invite you and welcome. We'll be happy to welcome you in the department in NIT Durgapur. Because I understand you frequently come to Tata Steel, Jamshedpur, so definitely it's very nearby, and we'll be happy to have you among us in our department, and we'll like to have your advice for the development of the department.
Yeah.
Thank you, sir, once again for your very nice presentation and good time we spent with you.
Robin, continue. Robin.
Thank you, sir. Thank you for clearing our doubts on all participants with so much tender and dedication. I hope it will help them in their field of work. As coming to an end of the technical season, I would request Mr. Syed Abdul Rahman, the President of IIM NIT Durgapur Student Chapter, to give the vote of thanks to our renowned guest and speaker of today's talk.
Hello, and my greetings to all. I, on behalf of IIM Students Chapter, NIT Durgapur, would like to extend my heartiest gratitude to Professor Bhadesia. Thank you so much, sir, for your talk today, and thank you for all the motivation. We hope to have many more interactions with you in future too. I am grateful to Professor Viswajit Haldar and Mr. L. Badu for attending this webinar with us. I would also like to thank all the members of the organizing committee for making the arrangements. Our faculty advisor, Dr. Arup Kumar Mondal and Dr. Madan Mohan Ghosh, HOD MME Department, for their continued support. Last but not the least, a big thank you to all our guests and attendees and my fellow classmates for being a part of this event today.
Thank you.
Before we end, just a quick announcement. The attendees who are interested in receiving a participation certificate for today's event are requested to draft an email with their name and other details to iimsc.nitdgp@gmail.com. That's it. Thank you so much. Thank you so much, sir.
Okay. Bye-bye.
Bye-bye. Thank you, sir.